Good afternoon. Okay, Chem 1A. We have talked about bonding, and we've seen there are different kinds of bonding, and we've talked about G. N. Lewis and his dot structures, that you can sort of see what electronic configuration you have when you bond two atoms together or even three together. And so this concept was that we only look at the valence electrons. These are the outermost electrons. The other ones, there's nothing changes. And we assume that bonding happens with the outermost electrons, with the valence electrons. Okay? So that means if you're in each period, if you're in the same group of two periods that are below each other, or any of the group, they have the same valence configuration, just in a higher energy, in higher orbital. Okay? So, thank you. You see that hydrogen has one, and it wants to be in a duet. So when it bonds to something, it will fulfill what we call the duet rule. And then lithium wants to probably fulfill an octet rule. Okay, octet, that it forms a stable octet. As you see, helium, neon, argon, krypton, xenon, radon, these are noble gases, and they have always the filled valence orbitals there. Okay, there's nothing more you can cram into here. And this is a stable configuration. And atoms and compounds try to get to a stable configuration by sharing electrons or pulling electrons away from another atom or adding another electron. And such adding an electron. Okay, so we talked about, let's see what I got here. We talked about lithium. Lithium has how many valence electrons? 1. And fluorine has 7. It's the second to last here, 7. And so and then we talked about electronegativity. We have a very large difference in electronegativity between the binding partners, speaking German, between the binding partners. You see that the more electronegative pulls that electron away from the more electropositive or less electronegative. So if there's a large difference in electronegativity. So we've seen that the fluoride pulls the electron away from the lithium, and it becomes itself a stable octet. That's the fluoride ion. And the lithium is now also a stable octet because it has the configuration, then if you look at lithium here, it has the configuration of helium when it lost that electron. So with this you have a positively charged cation and a negatively charged anion, and they attract each other through Coulomb forces and form the bond. The same is true with sodium. Sodium is just in a different period. 1 valence electron, and chlorine also has much more electronegative than sodium. It pulls that electron away, makes a Cl- ion, a chloride ion, and a sodium plus. And with covalent bonding, is it, for example, if you have here hydrogen and hydrogen, makes H2, so this brings one to the table or to the bond, this brings one to the bond, so this has 2 and this is 2. There's equal sharing. Equal sharing is perfectly covalent, and this only can happen with atoms of the same kind. So if you have Cl2, the same thing. Chlorine has how many valence electrons? Chlorine, 7, so it needs 1. They come together. You have 2, 4, 6, 7, 6, 8, 2, 4, 6, 8, they form an octet. And there are, of course, exceptions to this rule. You have CH4, hydrogen has each 1, and carbon has how many valence electrons? 4, okay. So this one, they share 1. This has 2, this has 2, this has 2, and this has 2. And the carbon has 2, 4, 6, 8. Remember, one dash stands for 2 dots, all right? Ammonia, there's a free electron pair, NH3. So the hydrogen has 2, 2, 2. And the ammonium, what is the number of free electrons it has available in the valence orbital? 5, okay. 2, 4, 6, 8. This is 8 now. It has a stable octet. Now with oxygen, it's a double bond. 2, 4, 6, 8. 2, 4, 6, 8. Double bond, right? It's a stronger bond. With nitrogen, it's even a triple bond. 2, 4, 6, 8. 2, 4, 6, 8. Okay, both have the octal. With carbon monoxide, so carbon has 4 and oxygen has 6, so they have a total of how many electrons? 4 and 6 is 10 electrons. That's how you count first the number of electrons, valence electrons that you distribute. And then you distribute them according to the duet and the octet rule. And so you have carbon has 4, so it's 2, 4, 6, 8. Carbon has an octet, and oxygen has 6, so 2, 4, 6, 8, also an octet. So we have a triple bond. All right, there are exceptions. I told you that xenon, these noble gases, and xenon is one of them, they are noble. Until the early 60s, it was believed that they don't react with anything. And along came our colleague Neil Bartlett, and he made xenon tetrafluoride. And there was the noblesity was gone, okay? So it could react with very aggressive compounds with fluorine, for example. Fluorine is a very strong electron acceptor, likes to pull electrons away. And so fluorine has how many valence electrons? 7. So there are 2, 4, 6, 8. 2, 4, 6, 8. See, I was lazy. I didn't draw the ones which don't do any bonding. So that's how you can do that, is you know how many electrons you have, okay? And so these are all have the octet rule fulfilled. But xenon has 2, 4, 6, 8, 10, 12. That's not the fulfillment of the octet rule, okay? That's called an expanded octet. It's a very much expanded octet. It's by 4 expanded, and this is a stable configuration, so we have exceptions. Rules always have exceptions, okay? Natural laws don't have exceptions, but rules have exceptions. Now, if you look at boron and fluorine, so this is boron trifluoride. So fluoride has 8, 2, 4, 6, 8. Okay, 2, 4, 6, 8. Here I drawn them. You could have drawn them here too. 2, 4, 6, 8, 2, 4, 6, 8. But boron has how many valence electrons? 3. Okay, so there's not a whole lot of electrons we can distribute. There's 2, so in this bond, then there's 2, 4, 6. We should have 8. So it's also an exception. The octet is not fulfilled. So there are 2 missing. And so that means if you would have a compound that could donate electrons to this here, something like ammonia, this would slip right in there, form a bond with this free electron pair to the boron, and then would be ammonia-boron fluoride. It's a very reactive reaction. So there would be a lot of bang going on if you would do that. So sulfur hexafluoride. So this is mainly with fluoride, as you know. There's some expansion or some deviation from the octet rule. So this is always a question everybody should be able to answer now. And most of you have seen the solution. And so there will be 100% success rate with this one. But maybe you think about this, even if you've seen the solution. Think about it. And I want to know the Lewis structures of formaldehyde. Is it this here? Is it that here? Or is it that here? So I gave you already several hints how to do that, and I will give you some more hints if you need them to answer this question. Please start your clickers. It's not about really having the right answer. It's about understanding the problem, okay? Sometimes if you have the wrong answer and I explain it to you or you think a little bit more about it, I got it, all right? Helps sometimes even having it wrong because you think more. forget to click in. Preferably with the right answer. 440. Good. Well, let's see what the answer is. Yeah, you paid attention. But there's still 30% here. No. There's still a number who don't have it correct. I think you need to discuss it, but let me help you a little bit, okay? So what you need to do is you have that much oxygen, that many carbons, and that many hydrogen. You see how many valence electrons each of them has, and then you add them together, okay? And then you distribute them according to the duet and the octet rule. And so you need to count if you have pictures like this in front of you. And then, in this case, I can tell you that you don't violate the octet rule. Why don't you discuss this briefly? Not briefly, for 1.5 minutes. And come on, let's discuss it. Everybody got to have it right, especially since I had the solution there. That's called success. All right. So you have how many electrons in total? Valence electrons, 12. So you need to distribute those 12. You have 4 from the carbon, 6 from the oxygen, 1 from the hydrogen, but you have 2 hydrogens here. This is then 12, so you add it up. So now I have to distribute and count. So this one here, this is a little sloppily written. It should be a little bit over here, a little bit over here, but you know, you get the drift, okay? So you have 2, 4, 6, 8, 10, 12, 14. Wow. Okay, that's too many electrons. That can't be it. Now, carbon, what do you have there? 2, 4, 6, 8. Carbon, octet rule fulfilled. Oxygen, 2, 4, 6, 8. Octet rule fulfilled. Hydrogen, duet rule fulfilled. Hydrogen, duet rule fulfilled. Okay, what's wrong with that? Carbon has 2, 4, 6, 8, 10. Okay, so this is not the octet rule fulfilled. With carbon, you should fulfill the octet rule. Okay, so let's see. With hydrogen, duet rule fulfilled. Carbon, 2, 4, 6, 8, also fulfilled. Oxygen, 2, 4, 6, 8, also fulfilled. That must be the structure. Let's open. No octet, no carbon octet, and 14 electrons. There you go. All right, now today we're going to talk a little bit more about polarized bonding and polarization, and we also will talk about resonance structures. Resonance structures are structures, Lewis structures, where you can write more than one structure. And so we talk about this and then about bond order. Now let's, you see here, this was polarization. This is a covalent polarized bond, or polar covalent bond, okay? So why is there this delta here, and there's a delta plus here, and a delta plus here? Why is that? Because the electronegativity pulls the electrons more to one side, all of them. So this will be acting like a dipole, and if you put this in an electric field, this happens to be water, you put it in an electric field, so this is how you write the dipole vector. That's the vector here. That's the sum of these individual vectors here. They always go from the less electronegative to the more electronegative. There would be one here, and so the vector addition, this is the vector then, okay? And the direction always points to the negative side, and the delta is, you can write it this way or this way. But if you put it in an electric field, it will orient itself. It will orient itself to the opposite pole. This is how your microwave works, okay? Water is, as you see, is polarized, and your microwave, you have an oscillating microwave field. And so the water molecules start spinning around in the microwave because you're changing the polarity all the time of this field. And with this, they cause friction in the material there, friction with each other, and they heat up the material. They heat up the water because they're rubbing against each other, or they heat up your roast or whatever, your noodles. And of course, fat and so on doesn't have a good dipole moment. So the better the dipole moment is, the faster it heats up, and water has a very good dipole moment. This is how your microwave works. And there was actually, when the microwaves came out, there was this case where somebody had a little dog and wanted to dry the dog. And of course, it's not the water is not only outside, it's also in the cell. So it's not a good idea, actually. You never heard of that? It's not a joke, actually. Hurts. The dumbness of people, actually. That hurts me the most. Okay, so we have this, and I showed this to you. Remember that experiment where I bent water with this electrically charged plastic rod? And I could bend it. I could make the water have a curvature. I think it was seen up there quite well. Now, hydrogen chloride, this is a polar covalent. And so the dipole moment goes this way. You now get the drift, how to work with this dipole moment. And if you, in summary now, we can see ionic bonding is the more electronegative element captures the electrons. Covalent, the electrons are shared equally. There's only ideal covalent are only with the same kind of atoms in a bond. So Cl2 or hydrogen H2 or O2, this would be perfectly covalent electron sharing, and this is how the least of the compounds do that. But what 90 or 95% of the compounds we deal with are actually polar compounds. They are covalent polar, that means they have unequal sharing, and with this they have a dipole moment. You see, here's a depiction better of that HCl, and we did actually make HCl in this explosion we had. And you see the electronic cloud of the orbitals is more to this side and less to this side here. That's how this charge distribution is, and it's signified by this dipole moment vector here. Now, if you look at this, for example, you have here a partner and here a partner. Obviously, this partner, because the vector goes in this direction, is more electronegative than this one here. So there's one here and one here. So would that have a dipole moment? Yes, of course, because the sum of this is somewhere in between here. Okay, vector addition. Now, this one has 2 equal partners and 1 different one. So this one is even more electronegative than this one here and this one. So that arrow is much longer here. And this, of course, has a dipole moment. If you add this vector, these vectors has a dipole moment. Now, another case is where you have here the same partner than here, and it is more electronegative than your center atom. That means the moment goes in this direction, the other one goes in that direction. So it says right here it has no dipole moment because it cancels each other. Opposite direction and same magnitude cancel each other in vector addition. Now this one here goes also, if you add this up, it cancels each other because it goes in 3 directions. So let me ask you now a question. Which of the following molecules? What? It does. Oh, it does not have a dipole moment, okay? For years I've been showing the thing. Nobody ever noticed it, okay? Including myself. Which of the following molecules does not have a dipole moment? Is it this here, or this here? So this, what was this called? Carbon monoxide, carbon dioxide, and what was this called? We just had it. Formaldehyde, okay? Good morning. All right. Why don't you try to answer that question? So the electronegativity you can deduce from the periodic table. You know now how this works. You're still with me? You are, two of you. Okay? Oh, you're done already. How about you somebody tell me? I just finished, okay. Okay, so there is a 74%, that's this in the middle there, COO or CO2, and, are you sure about that? You are? Huh. Let's see. Why don't we discuss this one more time? Everybody has to have this right, okay? Please. It's not always the majority, but often it is the majority. Okay, don't forget to click in. You're losing people. I don't know what's happening here. Okay, yeah, I agree with you. That's a perfectly symmetrical molecule. And let's see what we have the solution here. What was that? Okay. So now this one here, the one vector goes to this side, and the other one goes to that side. Is that okay? Carbon and oxygen. So this one, and that one, that one. That means they have the same magnitude, that's the length, but opposite sign. So they cancel each other. Remember, momentum was the same thing. Momentum, we had one in one direction, one in the other direction. The one was positive, the other one was negative. It canceled each other. When we stopped the gas with the laser, for example, the gas, we cooled down the gas. We had a momentum transfer. So you don't need to know vector geometry in order to solve these problems. Okay. It might help though. So what does this mean? There's no dipole moment. A perfectly symmetric molecule. No dipole moment. Now this one here, of course, there's a CH. There's a small little bit, a carbon a little bit to this direction, a little bit to this direction. But this goes this way and that goes that way, so that cancels each other. Okay. And now the only one is the CO. This would be this one. Yes, it does have a dipole moment, a net dipole moment. Now carbon monoxide is carbon and oxygen, and the oxygen is more electronegative. And actually, this is wrong. it has a dipole moment, but in the opposite direction. That shows you that this electronegativity table, because the carbon and the oxygen are relatively close to each other, when you do the measurement, you find that if you use that electronegative principle, it doesn't apply. But for this class, it's fine if you say it that way, okay? Yeah, but I need to say this for some of you guys. Some of you said, this guy is totally wrong. And there are people also on the web, then they say, I know that carbon monoxide has the opposite dipole moment than he showed, okay? You know now the reason. But we're not going to go away from Mr. G. and Lewis, from Professor Lewis. So the answer was then this one here, okay? So for the reason of this class, it's fine. Yeah? All right. Now you have ozone. Ozone is how many molecules? 3. And what? 3 carbons? 3 oxygens, okay? 3 oxygens. And so there are several ways of writing this in terms of Lewis structures. So this would be 1 oxygen has how many electrons? 1 oxygen, how many valence electrons? And so we need 3 oxygens. We have 18, 3 times 6 electrons. This is 18 electrons. Remember, this is an 18 electron system. 18 electrons among 3 partners, okay? That's all you need to know, essentially. Then you can deal with systems like this. So